last lecture we were discussing various physical processes in quantum electrodynamics. We have seen that the first order terms in the S matrix do not contribute at all to any physical process. So as far as any physical process is concerned, the amplitude, the contribution to the amplitude from the first order terms is 0, whereas we have seen that in the second order there are several physical processes which gives non-zero amplitude. As an example, we were considering the Compton scattering, where E plus gamma going to E minus plus gamma going to E minus plus gamma, where the original electron had 4 momentum p, the photon had 4 momentum k, and the outgoing electron had 4 momentum p prime, and the outgoing photon had 4 momentum k prime. There are two diagrams which contribute to this process. These diagrams are given by, you have an incoming electron of momentum p, and then you have an incoming photon of momentum k. Then at the end you have an outgoing electron of momentum p prime, and then you have an outgoing photon of momentum k prime. There is a propagator from the point x2 to x1. We had also seen that you can have an incoming electron of momentum p emitting first an outgoing momentum of photon k prime, and then the incoming photon of momentum k is absorbed, and finally you get an outgoing electron of momentum k prime. So these are the two possibilities, and then we have evaluated the amplitude for one of these processes. So I denote S the term in the S matrix which gives non-vanishing contribution for this process to be SA, and for the second process to be SB. And what we have computed in the last lecture is we considered this initial state I, which is an electron of momentum p and a photon of momentum k, and the final state consists of an electron state of momentum p prime and a photon state of momentum k prime, and we have computed this term SA and I, and what we saw is that this quantity is equal to 2 pi to the power 4 delta p plus k minus p prime minus k prime times m a, where the Feynman amplitude m a is given by minus E square times U bar of p prime epsilon slash of k prime I S f p plus k epsilon slash k u of p. So this is what we have derived in the last lecture. We can do a similar computation, and then we can compute this quantity SB I, and this will be equal to 2 pi to the power 4 delta p plus k minus p prime minus k prime times MB, where the amplitude mb is given by minus e square times u bar p prime epsilon slash k I s f p minus k prime epsilon slash of k prime u of p. Okay. So I will leave it for you to derive this result. You can show in a very similar way that if you compute this amplitude, then at the end of the day you will get this to be equal to 2 pi to the power 4 delta p plus k minus p prime minus k prime times mb, where mb has this expression. Now things looks very simple. So finally this amplitude here is simply given by 2 pi fourth delta p plus k minus p prime minus k prime times m, where m is given by ma plus mb. The question that I would like to ask is there a simpler way to compute ma and mb given these diagrams? And the answer is yes. You can simply write ma and mb by just looking at these two diagrams, and provided you have a set of very simple rule to compute these amplitudes. So these rules are known as the Feynman rules, and then now you know, at least you can guess what can these rules be. Okay. Especially this term here represents the incoming electron. This term here, not directly, but it schematically represents the incoming photon. This term represents the propagator, and this term here represents the outgoing photon, and this term represents the outgoing electron. So however, there are these interaction vortices. That is why I said it is not exactly representing the incoming photon. It represents the incoming photon and the interaction vortex. So let us look at this term again. Okay. Let us look at this diagram. You have an incoming electron of momentum p, and you have an incoming photon of momentum k. They interact, and then finally you have a fermion propagator of momentum p plus k, and finally you have, and then you have an outgoing photon of momentum k prime and outgoing electron of momentum p prime. Let us write u of p for the incoming electron, write epsilon mu of k for the incoming photon. They interact, and for the interaction vortex you write minus I e gamma mu for the interaction vortex, or according to our notation it is plus I e gamma mu. Then there is a propagator, fermion propagator of momentum p plus k. So I have I s f p plus k for a fermion propagator, and then you have the interaction vortex, which is I e gamma nu. Then you have an outgoing photon of momentum k prime. For that I will write epsilon nu k prime, and you have an outgoing electron of momentum p prime. I will write it as u bar p prime. You can see that this is exactly what your MA is. On the other hand, you have the second diagram here, where you have an incoming electron of momentum p which emits a photon of momentum k prime here, and then you have a propagator with momentum p minus k prime. Finally, the incoming photon is absorbed, photon of momentum k is absorbed, and you have an outgoing electron of momentum p prime. So, let us follow the same set of rules. This will tell us that you have a u of p for the incoming electron, you have epsilon of k prime, epsilon mu of k prime for the outgoing photon here, and then there is this interaction vortex for which I will write I e gamma mu. Then you have a fermion propagator of momentum p minus k prime, for that I will write I s f p minus k prime, and finally the incoming photon is absorbed here, or there is an interaction vortex which I will write as I e gamma nu. For the incoming photon of momentum k, I will write epsilon mu epsilon nu of k, and there is an outgoing electron for which I will write u bar of p prime. You can see that the amplitude computed by following this set of rules is exactly this amplitude here. So if this immediately suggests a set of rules which say that if you have an incoming electron line of momentum p, you write u of p. For an outgoing electron, you write u bar of p, whereas for an incoming photon, you write epsilon mu of p. For an outgoing photon, again if you are choosing a real polarization for photon, you again will have epsilon mu of p, otherwise you write epsilon mu star p. Okay. For fermion propagator, you write I s f of q, where q is the propagator momentum. For each vortex, you write I e gamma mu. So interaction vortex. So if you follow this set of rules, then you can recover the amplitudes just by looking at these Feynman diagrams. What is left is, suppose you have a process where instead of a fermion propagator you have a photon propagator. Okay. So then you simply replace this ISFQ by, I will represent the photon propagator as df. So for photon propagator, you have minus eta mu nu, or I will write as df q mu nu, the mu nuth component of the photon propagator with a factor of I. Now suppose you have identical particles interacting, just like in the case of E minus plus E minus going to E minus plus E minus, then you have to take care of the minus sign because of the exchange interactions. Okay. So, when you compute the amplitudes, finally you have to add them with a relative minus sign if in case you have you have identical particles scattered with each other. So, you have to keep that in mind. So, in addition to all these things, you have to keep the exchange interaction -1 for due to identical. And then so you follow this set of rules, and then you write these in a sequence just the way we wrote some time back, and then you add the amplitudes appropriately by taking care of minus signs wherever it is required, and then you add all these amplitudes together, you will get the total Feynman amplitude for any physical process. There are a couple of things that that remains. One is that suppose you have a closed fermion loop. Then you have to write a -1 for every closed fermion loop, and then you have to take trace. So, we will see why you need a -1 and then why you need to take a trace in a moment. And finally, suppose the momentum of an interline line is not fixed by any of these. So the point is that at every vortex the energy and momentum has to be conserved. That is why I wrote here for the fermion propagator the momentum p plus k, and here I wrote p minus k for the fermion propagator. That is because at every interaction vortex the energy momentum is conserved. In case the energy momentum conservation does not fix the momentum for any internal line, then you need to integrate over that particular momentum. For example, suppose you consider a process like this. Okay. You have a photon of momentum k. All it says is that if the momentum here is q for this fermion, then for this fermion the momentum is k minus q. It does not say anything other than that. So therefore, in this process the momentum q for the internal fermion line is not fixed. Therefore, in those cases you need to integrate over all possible values of momentum. So, you need to write 1/2 pi to the power 4th integration over d4q whenever the 4 momentum for the internal fermion line is not fixed because of the not fixed at the interaction vortices. So you follow this set of rules, then you will recover, you will get Feynman amplitudes for any physical process that you consider. So let us now look why we need to have a -1 factor for a closed fermion loop, and then why we need to take a trace. So now let us ask the following question: when do we get a closed fermion loop? Let us consider this example of physical processes which contributes at the second order. So, which term in the S matrix at second order contributes to any physical process which has a closed fermion loop? Closed fermion loop means you can have some interaction vortices and this loop has to be closed. So if this is x2, if this is x1, that simply means that if there is a fermion line which is contracted from x2 to x1, then you again have a fermion which is contracted from x1 to x2. Or to state it more clearly, what do we have for the S matrix is this term, normal order product of psi bar x1 a slash x1 psi x1 psi bar x2 a slash x2 psi x2. The time order product of this quantity is what, which comes in the S matrix, and then you do the weak expansions. In the weak expansion you contract various terms, and then whenever you have this contracted with this, you have an internal fermion line. Now if to get a closed fermion loop, not only this has to be contracted with this, this also has to be contracted with this. This is the case when you will get a closed fermion loop. So let us consider this term and then write it in a simpler way. So let's write, so that you have normal order product, and then I can expand it in terms of its components here. Okay. So I will call this as psi bar alpha of x1, and a slash is nothing but a mu of x1 gamma mu of alpha beta, and then you have psi of x1 which is psi beta x1. That is for this term here. Then you have psi bar x2 psi bar let us call it as eta x2, a slash is again a nu of x2 gamma nu of eta rho psi rho of x2 with this normal ordering. Now this is contracted with this, so you have a contraction here, and this is contracted with this. Now in this contraction I can just pull it to this place, but you have to keep this in mind that in this process it crosses two so if you pull it to the front, let us say you want to pull it to the full front, then it crosses 3 fermion 1 2 3, therefore it will gain a minus sign. So this is equivalent to writing minus 1 normal order product of psi rho of x2 psi bar alpha x1 and gamma mu alpha beta psi beta x1 psi bar eta x2 gamma nu eta rho, and then a mu x1 a nu x2 normal ordering. Now this is contracted with this and this is contracted with this. So what you get here is now this term is equal to minus 1 normal order product of this is just ISF x2 minus x1 rho alpha and then gamma mu alpha beta then psi beta x1 that this contraction will give me I SF x1 minus x2 the beta ith component of that and you have gamma nu of eta rho then a mu x1 a nu x2 normal order product or this is nothing but minus 1 ISF x2 minus x1 a slash x1 ISF x1 minus x2 a slash x2 this whole thing rho th component summed over and normal order product. This simply means that you take this quantity and then you take the trace of this. So, this is nothing but trace of normal order product of the whole thing. Okay. So, you saw now how why there is a trace and how did we get a minus 1 factor. So, this result will hold whenever you have a closed fermion loop. So, for every closed fermion loop you have to write a factor of minus 1 and then you have to take the trace appropriately around the closed fermion loop. All right. So, now we have the set of rules. What we will do is that we will consider a couple of more physical processes and then compute the respective Feynman amplitudes for those processes. Any question after this? So, let us say we consider this E minus plus E minus going to E minus plus E minus of momentum P1, P2, here the momentum of outgoing electrons are P1 prime and P2 prime. We have already seen there are two diagrams which contribute to this process. For one of them you have incoming electron of momentum P1, outgoing electron of momentum P1 prime, incoming moment electron of momentum P2, outgoing electron of momentum P2 prime, and then you have a photon propagator of momentum P2 minus P2 prime. Let us see. The other process that gives a contribution, the other diagram which gives a non-zero contribution to this physical process is again the same, except that the P1 and P2 primes are interchanged. So, you have P2 P1 prime, the P2 minus P1 prime P1 P2 prime. So, how will you write the amplitude for these two processes? This I will call as MA, the Feynman amplitude for this one is MA. So, you start, let us say from here you have an incoming electron of momentum P2, I will write this as U of P2, okay. And there is an interacting vortex here. For this I will write I gamma mu I e gamma mu then you have this outgoing electron of momentum P2 prime, I will write U bar P2 prime for this. Then you have a photon propagator for which I will write as I df, let us say this is k, I df of k mu nuth component. Then you have here you have an incoming electron of momentum P1. So, you write U P1, you write I e gamma nu for this interaction vortex, I e gamma nu, and then you have U bar P1 prime. Okay. So, our MA is given by this. What about MB? MB here I can write it as first of all, because these are identical particles, I have to write a minus sign, the phase vector arising because of the exchange interaction, and then I will follow the set of rules that we have here, and then write down the amplitude. So, this is P2 U P2 I e gamma mu, and then U bar P1 prime. Then you have a propagator I df k, which is P2 minus P1 prime here, let us call it as k prime. This is k and this is k prime. So, I df k prime mu nu. Then you have an incoming electron of momentum P U P1 I e gamma nu U bar P2 prime. So, this is the amplitude for this is the contribution from the second diagram, and then the total contribution here is M is MA plus MB. Okay. So, what about something with a closed loop? Let us consider the electron self energy diagram. You have an incoming electron of momentum P, and you have a fermion of momentum Q, a photon propagator momentum K. So, Q is just P minus K. 4 momentum is conserved at each vortex, therefore, you again will have an outgoing electron of momentum P. So, what is the amplitude for this process? You write again U P for this, then you have an interaction vortex I e gamma mu, you have a fermion propagator which I will write as I SF Q, then you have a photon propagator which I will write as I dF K mu nu. Then you have this interaction vortex for which I will write I E gamma nu, and you have an outgoing electron, I will write here U bar of P for the outgoing electron. Is this all? That is not all, because the K here is actually not fixed by this process, therefore, you have to integrate over it. Therefore, you just consider 1 over 2 pi to the power 4th integration d4 k, well, you should keep in mind that this q here is p minus k. So, this gives the amplitude for this process here. So, that way you can consider any physical process, you write down all the Feynman diagrams for this process, and then you can, from the Feynman diagrams, you can just derive these amplitudes by following the Feynman rules which we have stated. Okay. So what we will do now is, we will consider, now we know what is actually how to compute the Feynman amplitude. So the next question that we would like to ask is how to compute the cross section for a given process. So to compute cross sections, we have let us say you suppose okay, we will do this by considering example. So first what I would like to do is, we will consider the Compton scattering again, which we have studied in great detail, and then we will compute the cross section for the Compton scattering. Then we will follow this process, electron scattering, and then I will compute the amplitude at lowest order for this process as well, and then we will see how to do that. So let us look at the amplitude m here. It is given by minus e square u bar p prime epsilon slash k prime I S F p plus k epsilon slash of k u of p minus e square u bar p prime epsilon slash k I S F p minus k prime epsilon slash k prime u of p. So I can write it in simple terms. I can substitute for the fermion propagator. So this is minus I e square u bar p prime times epsilon slash k prime. For the fermion propagator, I have a 1 over p slash plus k slash minus m, here epsilon slash k, and then from the second term I get epsilon slash k prime 1 over p slash minus k prime slash minus m for this propagator here, and finally this is k epsilon slash k prime u of p. That is all we have. Then the cross section, we have derived a formula for the cross section in one of these earlier lectures. So, let me write down the differential scattering cross section for this process. This is given by 2 pi to the power 4th delta of p prime plus q prime minus p minus k mod m square, then m divided by 2 p dot k dq k prime over 2 k 0 prime 2 pi cube, then m dq p prime over p 0 prime 2 pi cube. You have an outgoing bosonic particle and one outgoing fermionic particle. So, accordingly your normalizations actually differ here, and then you have this appropriate factor which we have derived in one of these earlier lectures. This is the scattering cross section, differential scattering cross section. What we will assume in addition is, we will consider the initial electron, the incoming electron to be unpolarized. So, when it is unpolarized electron initially, what you need to do is, you need to average over its polarization. Okay. So, unpolarized so both the spins are equally probable, therefore, you just average over the initial electron spin. Then we will also assume that the polarization of the outgoing electron is not detected. Okay. So therefore, what you need in the cross section is that you have to sum over all the outgoing spins, all possible spins. Polarization of outgoing electron is not detected. This simply suggests that you need to sum all possible polarizations of the outgoing Okay. So this simply says that you need to sum over all polarizations R and S, I will say, because of this averaging you need to have a factor of half. This is the differential scattering cross section. Then what we will further do is, we will integrate over this outgoing electron here, outgoing electron momentum, and then finally what we will see is that what is the differential scattering cross section when the outgoing photon momentum lies in some solid angle d omega. That is what we are interested to compute. Okay. So which we will do in the next lecture.